So hi everyone, I'm Junming and today I'm going to introduce the project of MTK GHC port, namely using MTK garbage collection in GHC. So the talk will have about 4 parts. Firstly, I'll briefly talk about the motivation of the project and what is MTK. And then we'll have a look at our MTK GHC port, including our development pathway, the current status and results. And then I'll talk about some of the challenges and key takeaway lessons behind the project. So first, people might be wondering, why are we interested in the port to use MTK if GHC already has a sophisticated garbage collector? Well, first, the port can provide Haskell users with MTK GC algorithms, and it also can provide developers and researchers with an alternative, flexible, and credible platform to develop GC algorithms for Haskell. The port development also helps to bring cleaner and more modular structure to GHC runtime, and even if no one is using MTK at all. Here, I would like to emphasize that our port does not replace the current GHC storage manager, but it's rather an alternative to it. So what is MMTk? MMTk stands for Memory Management Toolkit. It is a research-oriented, general-purpose toolkit for different language implementers. It's led by Professor Steve Blackburn, and the team is based in the Australian National University. MMTk was originally written in Java as part of the GHC RVM Java runtime, and it's now rewritten in Rust to be a generic library. MMTk aims to provide a large selection of garbage collection algorithms that can be used by different languages with different infrastructures. While being language agnostic, MMTk also aims to provide GC algorithms with high performance. So currently, MMTk has a series of ongoing imports and a range of GC plans. And here, and for the rest of the talk, we'll use the term GC plan to refer to a particular memory management strategy. So our GHC port project started about a couple of years ago. We firstly started with refactoring some of the GHC runtime by identifying and removing some dependencies on the internal storage manager. The major dependencies we modified were about GHC block allocator, block descriptor structure, the per generation thread list, and weak pointer lists. Next, we started the port with a no GC plan, which is a garbage collection plan that only does allocation using MMTk without any collection of memory. Although no GC is kind of not a practical garbage collection, this phase served as the focus on finding out how we can use MMTk for memory allocation in GHC. So this gives us the first key component of the port, that is where we teach GHC to know about MMTk. For example, how to use MMTk for allocation. So there were 2 sources of allocation that we touched in this phase. The first one being large objects and array allocation, which occurs in the runtime system. And the second one being allocation of small objects, which occurs in the generated mutator code. So we used the bump allocator, that is an allocation structure that both MMTk and GHC use. In this way, we kept the same semantics of bump allocator as we have in the current GHC runtime without any major changes to the GHC code generator. So in the next phase, we added support for a non-moving plan. In our case, we used the non-moving IMIX plan. This introduced another key component of the port, that is to teach MMTk to know about GHC. For example, how to do object scanning and weak pointer tracing. In our port, we wrote a fairly type-safe object model for GHC closures in Rust to support scanning. For the result, currently we can compile standard Haskell files with -mtk flag. Our modification allows the user to choose between either MTK or the GHC storage manager. We are able to use GHC to compile Cabal under MTK, and we managed to run the GHC test suite under MTK with majority of the tests passing. So to summarize, our development pathway thus far includes the refactoring phase, the Node.js phase, and the non-moving emix phase. And currently, we have turned our focus to the moving plan, where our main task is to introduce forwarding pointer mechanism in the port. And after that, we plan to introduce the generational GC, where we need to add write barrier in the port. And then we can have some comparisons between MTK and GHC internal storage manager that is also using generational GC, such that we can perform some evaluation measurement to get some concrete performance result. As for the challenges, one of the most interesting and perhaps difficult part of the implementation is weak pointer tracing, as the algorithm is quite subtle. And build system integration was also a difficulty in the project, as we have to integrate the compiling of Rust programs into the build tree. Another main difficulty for me was to decouple GHC's storage manager from the runtime system. There were dependencies, or in another word, abstraction leakage, which made it difficult to introduce generic modules like MTK. This issue is not specific to GHC, but exists in almost every language, which where components coupling and dependencies were designed to bring optimization. This also leads to a more general question idea behind MTK's philosophy and research purposes about software design. We usually think of balance between modularity and performance and components coupling, where MTK's goal is to have a generic memory management platform that can achieve both modularity and high performance. And MTK actually has demonstrated that this goal is achievable in the OpenJDK port, and currently developing GHC port will certainly contribute to the solution of a high performance generalized memory management framework. Lastly, I would like to thank Twig.io for the initial funding, Steve and ANU for their continuous support for the project, E for his help into MTK's internals and the entire MTK team, and Ben, who worked with me throughout the project. And thank you so much for listening. Here's a link and QR code to the project repo if you're interested.
Excellent. All right. Thank you very much, Junming. All right. So do we have questions from the audience? Simon.
So thank you for such a nice talk. I'm really enthusiastic about this project because garbage collection seems like quintessentially an example of something which is a quite complicated task with lots of different algorithms and tens of person years of development time that you could potentially share between languages and implementations, but which we tend to have bespoke garbage collectors for everything and just get Ben to implement a non-move. So it seems like a great plan. But it often stumbles on the details that you didn't say very much about, like that we use GHC's garbage collector to perform all sorts of sort of services that the rest of the implementation needs. You mentioned weak pointers is one. Another one is shorting out indirection nodes, which are created when we update thunks. Another is that when we've got a pointer to a fully evaluated thing, we then take the tag bits from the thing we're pointing to and put them at the tail end of the pointer. And I'm sure there are 3 or 4 other things that I'm not thinking of that it's hard for me to see how we can how you can be sure you can get all of these things going while still maintaining the abstraction barriers and modularity that you described for MMTK. So you must have talked about this endlessly with Ben. Do you want to just say a bit more about some of those challenges?
I think for the details, so we put quite a bit of GHC specific code in the port. While this can be specific, the MTK code itself is language agnostic and is modular, but we do need a per language port for to glue the parts to adapt to, I guess, different frameworks.
To expand upon that. There we are. To expand upon that a little bit, you certainly do need to have a very robust bit of code that is GHC specific. I mean, it is the majority of the work that we put in was in fact Rust code written to teach MMTk about the specifics of GHC's object layout, the fact that we have tag bits, the fact that there are this ability to do forwarding pointers, and rather for object interaction shortcutting, and all of these things, it turns out, actually can be fit pretty cleanly into MMTk's existing framework. That's not to say that all of them are, and there are certainly weak objects or something we're still sort of struggling with. Deadlock detection in particular, which is a rather tricky one, is something that we don't, I'm not, I think, fair to say neither of us are particularly happy with the design as it sits currently. But these are things that the MMTk team has been very eager to discuss with us, and this is a living project. So both sides are adapting to meet each other's needs.
So it's going to improve MMTk as well.
Yes, absolutely. Okay. Yeah, we've already been upstreaming. So and
selector thunks as well.
Selector thunks, yeah, that's right. But we did, yes, yeah. Selector thunk, yeah, yeah. So yeah, I think most of the functionality is actually there. There's a question of whether it is as cleanly implemented as you'd like, and that's another question. But functionally, I think it's actually quite good. It turns out that pointer tagging is actually quite important for correctness nowadays, as well as it's more than just an optimization. So you can't really get away without it.
Just a naive question. There, at the start of the day, there was a JavaScript backend to GHC. So presumably the V8 runtime doesn't have support for weak pointers and so on. So is there a completely different layer of translation happening for the JavaScript backend that lets it work in a totally foreign GC than what is happening here with the GHC storage manager? Or is that just allowed to leak and you don't really care?
Sounds like a good question for Leute, if I'm not mistaken.
It's totally different, but we do struggle to implement some things. Like V8 does have weak pointers, but the GC weak pointer tracing algorithm is very unique to it. And we probably can't ask for specifics in the JavaScript runtime. We were thinking of introducing a different kind of weak pointer with slightly different semantics that allows it to run in the JavaScript runtime, but maybe there's an opportunity for WebAssembly, since currently the WebAssembly backend starts with CMM and works with, it compiles the GHC garbage collector to WebAssembly and does its thing there, so that works the same. But the future of WebAssembly is that they add a managed runtime, and there I just sent to my teammates the idea that the lessons from MMTk we really should send to the WebAssembly team to see that if they can make WebAssembly GC suitable for Haskell. I hope we can work on that in the future. But it's complicated. But
if I'm not mistaken as well, you can probably compile MMTk to WebAssembly if I'm not, or to maybe within script, and I'm not sure whether that's So. Well, yeah, you don't get to use the native garbage collector, but yeah, great. One more. Oh, we're out of time. Yes, of course. All right. Apologies. All right. Thank you very much. Hear it again for Junming.